Start.
Hello, everyone. Good morning from Taipei. I'm Yanhuan Li, a program committee member and an assistant professor at National Taiwan University. We're happy to have Jason Lee to give us the lecture this morning. Jason is an assistant professor at Princeton University. He received several awards, including the NeurIPS 2016 Best Student Paper Award, Sloan Research Fellow in Computer Science, and ONR Young Investigator Award. Jason is working on the foundations of deep learning, representation learning, and deeper reinforcement learning. In fact, if you're working in these areas, you must have read many papers co-authored by Jason. Jason will be talking about the theory of deep learning. If you have any question during the lecture, please type it on the live page, and Jason will answer later. Jason, please start.
Okay, yes, thank you for the invitation. Sorry I didn't make it to Taipei this year. Hopefully next time. So today I'll talk about beyond linearization in deep learning, which is a core topic in the optimization and generalization in deep learning. Right, so I'll just get started. I'll start off by telling you what I mean by linearization in deep learning, which is a recent analysis tool developed the past two or 3 years. And then I'll talk to you about several ways to go beyond linearization, some recent results in this area. And finally, I'll end with some open directions. Of course, feel free to type your questions in the chat, and I'll take them as we go along. Okay, so today I will focus on optimization-based algorithms, essentially gradient-based algorithms that minimize the training loss. So, for example, I won't really talk about other methods you could use to learn the neural network, such as like spectral methods or tensor methods. I'll focus on methods that use something that looks like gradient descent or stochastic gradient descent. So essentially, you can group the proof techniques used to analyze gradient methods into 3 classes. The first class only uses essentially the gradient is non-vanishing, and thus you make progress, like sort of in gradient descent, the fundamental, the descent lemma tells you that you improve at least by the norm of the gradient squared over 2, let's say. Order of the gradient, norm of the gradient squared. So if everywhere you hit, everywhere you encounter the gradient norm is non-zero, then you must make progress. You can only make a finite amount of progress because the loss is lower bounded at 0. Like, for example, you start at loss value order 1. You know that the loss is lower bound 0. So if you make progress every step, then eventually you terminate and it's a global min. That's kind of the first type of proof. The second type, roughly speaking, will use some higher order derivative information. Generally, it will be second order derivative information, although the algorithm may not. So these include proofs that I'll go into some detail later what I mean by this, but these include things that use like Hessians, at least in the analysis, but the algorithms are still gradient based, but then they implicitly use the Hessian in the proof. And then finally, some even more complicated proofs will explicitly analyze like the order of learning. Like they'll say things like, first you learn good features, then after you learn good features, you learn a linear classifier on top of those features. So they talk sort of explicitly about training dynamics. Okay, so sort of, let's talk a little bit about what kind of proofs, what kind of problems fall into each category. In the first category, you can think is roughly like all of convex optimization, right? So like, what is convex optimization? It's basically saying in unconstrained convex optimization, you know that all stationary points are global mins. So then basically, as long as your gradient is not 0, you're not a stationary point, so you're not a global min and you make progress. And then the only way you gets stuck or a gradient descent stops is if you reach a stationary point. So then that must be that you reach the global min. So then, all of convex optimization is essentially in the unconstrained convex optimization, like linear regression, logistic regression, so forth. Single index models, these are sort of like one neuron models plus well-specified. These kind of models, they satisfy, if I define this to be the loss function, these kind of satisfy that, essentially they satisfy this kind of one-point convexity condition here that kind of you point towards the minimizer. And this kind of implies you move in the correct direction for the minimizer. Star convexity is very similar. Most local convergence results are in this category 2 of also that you only kind of use the gradient information. Okay, so of course, it's a big category in the sense that it contains like many, most of convex optimization, but still it won't include things in the second category. So matrix factorization, matrix completion, like any loss function that looks like this. This is obviously not convex. It has U times V. That makes it non-convex. It has critical points that are not global, like U comma V equals 0, 0 is stationary point, but not global. So in fact, there's a lot more stationary points. I'm just giving one example. It's also a pretty big category, tensor decomposition, phase retrieval. And most of these avoiding saddle point problems fall into this category. So the trick in category 2 is you usually want to use some information like at these stationary points, there exists second order descent directions, and then that allows you to kind of escape from these. Okay. So category 3 is more involved and usually involves very specific analysis to the problem setting. Generally, you need some specific assumptions on the conditional distribution of Y condition on X, sometimes even assumptions on X itself. For example, we have a proof with Jeff Hao-Chen and Colin Wei and Tenyu Ma about label noise SGD and how this noise causes you to learn things in the correct order. You first go from a large initialization towards 0, and then you do some sort of stage-wise learning. A lot of the papers that leverage hierarchical structures, these 3-layer networks that show you can do feature learning, backward feature correction, ResNets, sort of this learning orthogonal ReLU networks, the benefits of large learning rate, these require this sort of what I call a category 3 proof. And they essentially look like, roughly speaking, you want to chain together steps of category 1 and 2. Category 1 and 2 with careful induction and argument about learning order. You first kind of like in each stage, you would use a proof from one of the prior categories, but then you have to carefully combine them and to show like once one thing is learned, it helps you learn the next thing. That's kind of the rough idea. Okay. So today I will basically skip category 3 as it's kind of not so easy to describe in a 1-hour lecture, and it also is very specific. I'll essentially cover categories 1 and 2. And I'll first start about category 1, and it's essentially what I'll call the linearization principle. Okay. So linearization is, of course, not specific at all to deep learning. It's in fact something I'm sure everyone's here knows. It's simply just Taylor's theorem. So for the rest of this lecture, f theta of x will be my neural network. Okay, some nonlinear function approximator, but typically a differentiable nonlinear function approximator. But essentially, it'll be a neural net for the rest of the talk. So I Taylor expand around f theta 0. I'm going to just pretend this is like close to 0 for simplicity. Then this is the linear term. I'll call this the linear term. And this is like a higher order term. A higher order in the distance that theta moves. Okay. So my working assumptions for now will be the second order term is negligible. I'll basically argue this is negligible and this is negligible for now. And let's see what happens if you pretend it was actually just this. And this function, I'll call it f linear of x, is linear in theta. So there's some, this technique, at least in the context of deep learning, I don't know when it was first used. At least it's been used since my paper, one of my papers with Soto Kotabi, Javin Martin Lee in 2017, I think. It's at least as old as that. It might be older. And there's nothing special. It's just Taylor's theorem and using it. And then more recently, this has been interpreted as a sort of a kernel viewpoint due to Jacob, some of my work with Simon Du, Sanjeev Arora's group, Shazad and Bach, numerous people listed here. Okay, so what is this kernel viewpoint of this linearization? Like I said, let's consider only this function, and it's linear in theta. So you can think of it, this as like a feature vector. So it's the length of the parameters, and it's the feature induced by the distribution of theta 0 and x. So of course, as we all know, if you train a classifier that's linear in some feature space, this induces a kernel where the kernel entries are given by phi of x dot phi of y. And when it happens that this phi is chosen as this is known as the neural tangent kernel. Okay. So the neural tangent kernel, let's say you have a network where theta is the parameters. So these w's correspond to the thetas. And then you have, okay. And then what you do is you differentiate with respect to the w's, and you get a kernel for each group of parameters or weights you differentiate each of these. And each one gives you a kernel. You take some linear combination of them induced by the initialization sizes and things like that aren't very important at all. And you get a kernel here. So just as the form of the kernel itself is not very informative. So this is something, this one is old. It's been at least since Radford Neal's work in like 95. This kernel was first introduced by Jacob, although it's just equivalent to the Taylor series viewpoint, 2018 or 19. Okay, so this is sort of this kernel. So like I said earlier, it doesn't matter a lot how you initialize. Depending on how you initialize the weights, you can get different kernels. So for example, in this first initialization scheme, you get what's known as the random feature kernel, just this one right here. If you initialize in this way, which has now been called NTK parameterization, notice the key thing is you pull out the 1 over root m here. Instead of AJ being 1 over root m, it's been pulled out explicitly. In this case, you get a sum of K1 plus K2. You can also consider just training the W's and you get only K1. Okay, so this is not very important. the only message here is that you should think of this NTK as a family of kernels. It's not a single kernel. And then a lot of this earlier work by Rahimi and Radford Neal's group, Dan Lee, they study this special case where only K2 matters and many of the other terms. And in the Bayesian literature, this was also studied, called NNGP, neural net Gaussian process kernel, I think. Right. Okay. Sometimes for theoretical analysis, it's convenient to look at the infinite width limit of these kernels. For depth 1 and depth 2, this is actually very easy to compute, and it's more tedious for deeper layers. And these have, explicit closed forms in terms of trigonometric functions, their inverses, and the norms and the inner product. The inner product x transpose x dot x prime. And these kernels are radially symmetric if you use a Gaussian initialization. And it's a feed-forward net, a fully connected net, sorry. Okay. They have a closed form. I am not actually going to go into this. This is not important for what I want to get across. The message I want to get across is actually that the statistical behavior of NTK, the neural tangent kernel, is not very impressive. It only is as good as, say, a Laplace kernel, which is roughly not too different from a Gaussian radial basis function or a polynomial kernel. And I'll give you more precise statements of the statistical behavior of this kernel in the second half of the talk. In my view, where the linearization principle shines is not the statistical aspect, but its power in analyzing non-convex optimization and why over-parameterization allows you to do optimization in polynomial time. Okay, so I won't say anything more about these kernels, except to say that their statistical behavior is not very good. However, I view them more as a proof technique for optimization. Okay. All right, so let me talk about the simplest non-convex optimization problem in deep learning theory. So I'm going to, for this section of the talk, I will consider two-layer neural networks. These are parameters and these are parameters. This is any smooth activation. Actually, ReLU is fine to it. It's basically anything you want. The loss function will be square loss. Actually, the proof works for any convex loss. Okay, for simplicity, I'm only going to train the W's. So this is a non-convex problem, right? Minimizing with respect to W of Y minus summation J, AJ, ReLU of WJ dot X squared as a function of W is non-convex. Okay, so how do we do this? So instead, we will consider a different surrogate loss function for analysis purposes. My algorithm will always be gradient descent on the original model. Now imagine that I look at this linearized model. So let me get some better notation. This is loss of W. And then I have a surrogate model where here I replace this with f hat theta of x squared. Okay, this problem here, in fact, is convex. And that's basically trivial. It's a linear model. This is just linear regression. In fact, the simplest convex optimization problem. Not only is it convex in theta, thetas are actually just W because I'm not training the A's. Not only is it convex, it satisfies the Polyak condition if the Jacobian of the network, J of theta, is a matrix, which is the gradient with respect to theta, data point 1, up to data point n. I have n training samples. Okay, so if this sigma min is positive, then we have, in fact, linear convergence, not just convex, in fact, converges linearly. So I'll now show you how to use the linearization technique to prove that gradient descent can optimize this two-layer neural net in polynomial time. In fact, in very fast time. And this proof sketch follows, like I said, a paper by Madi Sotan-Tokabi, Adel Javimard, and myself in 2017, which I think is the first usage of the linearization principle in deep learning. It predates the term neural tangent kernel, for example. Okay, so what do I need to show? I've already argued to you since that the loss function L bar, which used the network y minus fw hat of x, this one is convex. So if it's convex, gradient descent converges, and that's it. However, I have not shown to you that f hat is close to f theta, which means I have not shown you anything about the original loss function. Remember, my goal is to show GD finds global min of L, not L bar. Okay. So it's clear, it's absolutely obvious that if you do GD on L bar, you get a global min, just because it's linear regression. Gradient descent converges on over parameterized linear regression. That's a, essentially a well-known fact. Oh, and this Jacobian, I want to write the dimensions. It's the number of neurons m times the dimension by n. So it's a number of trainable parameters by n. I'll call p is m times d. Okay, so I need to show you this. And I'm going to aim for something slightly harder than just showing GD finds a global min. I'm actually going to show you GD finds a global min at a very fast rate, at a geometric rate. The way I will do that is by proving the Jacobian is positive for all theta encountered by GD. Okay. So these are the two things I want to show. And how I do it is sort of via, I break it down further into two steps. The first one is I will show that, remember J of theta is Jacobian. It's just, you take the gradients with respect to all data points. And you stack them. Sorry, theta and W's are the same thing. I usually let theta refers to all parameters and W's are like individual layer weights. But for two layers where we don't train the last layer, it's the same thing. So we want, what we're going to show is that, sorry, there's a typo here. Step 2 will show that J at random initialization is sufficiently positive. J of theta 0 is sufficiently positive. And then I'm going to show J of theta minus J of theta 0. So this is an obvious thing. This is just sort of, it's just because the Jacobians are the gradient, so then the second derivative, the Hessian, is the Lipschitz of the Jacobian, right? So then you'll have something like this. And then I'll actually show this goes to 0 as m goes to infinity. So actually step 1 is, this step is very easy. This is essentially, you can view this as a trick. There's nothing mathematically deep at all in step 1, in fact, I would say. Step 2 is more difficult. Step 2 requires some pretty hardcore random matrix theory. I just saw there's a question from Seung-Woon Yoon. The question is the linearization an assumption? How valid is it for modern deep neural nets? The linearization here is not an assumption, it's a proof tool. So the linearization is never used in the algorithm. The algorithm is gradient descent on the original network, not the linearized network. The linearized network is just something in the proof that we use to help us analyze the original network. It's a proof tool. So it doesn't really, it doesn't correspond to anything in reality at all. It's not like an assumption about reality. All the assumptions will be stated in a minute. Okay, so the first thing, I'll first prove the easy thing. In fact, you can almost just see the proof of this. If you just write down the gradient with respect to W of the network, it looks something like sigma prime of WX, X transpose. And you can see that if you subtract these two terms at two different values of W, you're going to get a term that looks like, just by the fact that, so this is just the maximal value of the derivative, 1 for most activations we use. A infinity norm, sorry, I forgot the A's here. That's obvious. You can see if you just subtract these two, that's going to come out. Did I forget? Sorry, this should be sigma prime prime. W minus W bar, that comes here. So this is just a simple calculation, essentially. Deterministic lemma that's true for any data. It did use the two-layer structure, but there's analogous lemmas now in the literature for any network. Okay. The more difficult lemma that we proved in this paper is that if the number of neurons is bigger than dimension, so remember X size, so now I make strong data assumptions. I'm going to assume this is normal zero identity, dimension D. If M is bigger than D, then sigma min of the Jacobian, so this is a pretty complicated random matrix, right? Remember, this random matrix looks something like, it looks like the Kronecker, each column is this is let's say the A's are 1 to make my life easier to write this. It looks like this Kronecker product X1 up to Kronecker product Xn. So notice the difficulty in this random matrix is that the X's are like, you don't get to control like every entry is random. The randomness goes through a nonlinearity and a W. So when M is bigger than D, we proved this. So what that means is that and this is positive because this guy is greater than 0. W0 is always initialized at random. So, sorry, I didn't even define W0 is. This is W1 transpose up to WM transpose. It's all the neurons in the network. Remember, the original function looks something like this. So I take those, I stack into a matrix. I'm calling that now Jacobian of W0. That's a complicated random matrix. Its minimum singular value, surprisingly, is bigger than the dimension times the minimum singular value of just the matrix W0 times the infinity norm of A. Okay, and then this is positive just because W0 is entry-wise Gaussian, let's say. So what does this say? So at the end of the day, what we have is if M is bigger than D and MD is bigger than N, and you have any full rank initialization, then gradient descent decreases the loss to 0, and thus can find a global min. So what these two things combine to say is that we don't explicitly show there's even a global min nearby. But what we do is we prove the loss decreases, it goes to 0 at a geometric rate, and we prove that WT stays near W0. So the only way that both of these things can be true is if there's a global min near W0. This analysis on the required width is sharp except this condition here. So MD bigger than n is absolutely necessary. Because the Jacobian, it needs to be a P by n. It needs to be a tall matrix. Otherwise, it's not full rank in the right way. And very recently, maybe less than a year ago, Zhang and Montanari proved essentially the same theorem in the other regime, in the m less than equal to d case, for random initialization. So it doesn't quite work, I think, for all full rank W. But regardless, you piece together these two theorems, and you get for MD bigger than n, and random init, and random W, you get global convergence of gradient descent, right? And so this is sort of can show you that this is a very powerful proof technique in optimization, right? I've shown you simply that sort of essentially a minimal amount of over parameterization. This is really the minimum. It's saying the number of parameters is only bigger than n log n. So off by only just log factors. This shows that gradient descent gets you a global minimum with minimal over parameterization, and it does it quickly. It does it at a geometric rate. I didn't discuss the rate, but the rate is actually easy to work out. So you can compare this to more recent NTK papers, for example, Du et al., Du and Zai, Du, myself, and Zai, and Wang, and Li. These papers here, which we're using kind of, so these papers, for example, and also the work by Alan Zhu, they showed, so they require things like m is bigger than poly of n, but the thing is they work for any data, right? They only needed like some separation conditions, essentially things like your data points need to be separated, but then you got bad polynomials. Maybe the best polynomial you can get here is like n squared, even after 3 years of sharpening these bounds. And sort of the reason here is there's no real random matrix that you can use. That lemma here, this lemma right here, did a lot of heavyweight random matrix theory, and this is kind of the reason you only need MD bigger than n. And similarly, this paper by Zhang and Montanari did some relatively difficult random matrix theory. And when these two, you glue together these two results, and you get parameters bigger than n is sufficient. Okay. Of course, you can look at the proof now, and in retrospect, you can see now that if you were willing to just assume the Jacobian random initialization is positive, then gradient descent still converges to a global min. The theorem still holds. The Gaussian data was only used in this one step to show this is positive and a quantitative bound. Okay. So essentially, this entire proof technique, the one part you need to fill in is proving this theorem for whatever random initialization and network architecture you use. this is also very different from these papers. In these papers, essentially, you even had that the finite width behavior approximates the infinite width kernel, which I think is going back to the question that Seng-Wung asked, is that this is unrealistic. That if you need so much overparameterization and such a small learning rate, then it is unrealistic to assume that the finite width approximates the infinite width, and experimentally that's false. So that's kind of what I like about the theorem from this paper, and also combining it with Zhang and Montanari, is you would have essentially at the minimal overparameterization, and this is true in practice, right? You can check the ResNets have 10 million parameters roughly. ImageNet has 1.5 million samples. So the number of parameters, remember this is number of parameters, is bigger than that. There's a question, let's see. Maximilian Thiessen is asking, is it possible to drop the Gaussian assumption? Yeah, in fact, Gaussian itself is not important. You need some isotropicness, at least to like, I believe, the fourth moment. Like you need this to look like a Gaussian to the fourth power. Like the fourth moment of your random variable needs to look like a Gaussian. Actually, there's a few other things. It's not so easy to answer this. But sort of like I said, this proof, the only thing that I use about Gaussian is this statement here. Any other method you can use to prove this is positive, this theorem still holds. Like I could say, cross this out, say, if sigma min of J at initialization is positive, and then I don't need any of this. I don't need any of this, actually. So this would be a true theorem. Like, and there's no reference to Gaussian at all here. If the Jacobian at init is positive, then gradient descent will decrease the loss to the global minimum value. Hopefully that answers the question. Okay. Okay, so that essentially summarizes what I want to say about linearization. So my key points here are: one, linearization should be really viewed as an optimization technique, not a statistical tool. It's not a very good statistical tool. Two, there's kind of this myth that you need a lot of overparameterization for linearization. That's not the case. You need a lot of width overparameterization if you want to show your finite width is close to the infinite width neural tangent kernel, but that's not needed at all in the optimization proof. That step is only needed in the statistics. So if you turn to this earlier paper, before the NTK stuff, in fact, it only needed this minimal width, which is a very realistic assumption. And essentially, what I hope you take away is that once you have the Jacobian is positive, the gradient doesn't vanish spuriously, and then it becomes just like convex optimization. Yeah, okay. Just want to see if there's questions. Okay, I think there's no questions. So I'll talk a little bit about beyond linearization now. And I'll say in 1 minute why, in my opinion, we need to go beyond linearization. So before I do that, let me make a brief interlude to a different question in deep learning theory. Not the optimization question, the statistical question. So sort of in my opinion, if you only look at optimization, in fact, linearization gives a very satisfactory answer, and there's not that much to be said anymore. Gradient descent, stochastic gradient descent, whatever you want, they all converge, and they converge quickly at minimal overparameterization. Okay. However, we must, as we are doing machine learning here, we need to consider also the statistical sample complexity. So this is sort of kind of the most basic, sorry, there's a question. Chukwuka is asking, I suppose linearization is the application of the kernel trick. If not, you can say more. I would not agree with that. I would say linearization is application of Taylor's theorem. The kernel trick is a computational trick. I'm not talking about computation. The algorithm is gradient descent. I'm not talking about how to make it more efficient. This has nothing to do with the kernel trick, I would say. The kernel trick is a computational tool, not an analysis tool. So I would just say linearization is Taylor's theorem. Like Taylor's theorem, meaning this is equal to at the random initialization plus the gradient. And then the idea is that we can analyze a network, call it this F-lin, and this induces a convex loss function. And that makes the analysis much simpler. And then we prove that regular gradient descent is close to gradient descent on this linearized network. Okay, so let me move back here. Right. So kind of the most basic question in deep learning theory, one of the most basic, is that I have a teacher network of small width of width R. And given data from this two-layered teacher, I want to learn to accuracy epsilon with respect to population loss. And then the question is, how many samples? Okay, so let's ask, let's kind of calibrate ourselves in terms of what would be a good result and what would be a bad result. So for this section of the talk, D equal input dimension, R equal teacher net width. Sort of just by an epsilon net parameter counting argument, you can see that the information theoretic sample complexity you need here is roughly D times R just by parameter counting. And you can get this, this is attainable if you allow yourself exponential computation time. Okay. A very good result, if you can do this computationally efficient, is maybe not instead of linear in D times R, to do it polynomially in D and R. And then sort of just as a baseline, let's look at how kernel methods do. So if sigma is a monomial or polynomial, or say a nonlinear activation, you can truncate it to make it of the accuracy epsilon. You would need D to the degree of sigma times R squared, roughly speaking. Okay, so we have like a variety of results here, from the best, slightly worse, and then this is what we know how to do. This we know how to do, this we don't, this we don't. Okay. And we know how to do all of them if you ignore computational time. Okay. In fact, we can turn to sort of the vast literature on lower bounds to see what we can or cannot hope to do, I guess. Yeah. Lower bounds are conditional on hardness conjectures. But short of breaking a hardness conjecture, there are lower bounds that rule out. So if you do not utilize any distributional assumptions, it rules out learning in polynomial in D and R. Like this is probably impossible, because if you could do this, you could solve things like Junta's intersection of half spaces, and probably even D to the little O of R. This is probably hard. Okay. So of course we shouldn't give up, but just because there's lower bound saying something is difficult, we shouldn't give up on this at all. But it does kind of inform us what assumptions we need here. And even there's distribution-specific lower bounds. So even if you let me assume that the x's were marginally Gaussian, there are some recent lower bounds in the statistical query framework. I won't talk about what that is, but essentially it says that even if your data comes from a ReLU teacher network of width R, you need D to the R queries. Okay, so like, it's kind of saying like, we cannot hope to learn this really better than D to the R, or your algorithm has to be really weird. We should keep in mind though that, lower bounds are not always real in a sense, that frequently minute assumptions can make these possible. For example, if you simply assume the singular value of W star is positive and the network is not too wide, spectral methods can do this. In fact, you can even do this with SGD by applying SGD on sort of a tensor decomposition problem. It can estimate the parameters also under this sort of under this distributional assumption plus this additional assumption. Okay. And in a sense, these seemingly break the lower bound. Of course, it has extra assumptions. The lower bound construction in these cases have this equals 0. Okay. So we can also turn to sort of what's a popular viewpoint in applied math. I'll call this sort of the functional analysis viewpoint, for the lack of a better name. In this viewpoint, we will write neural networks of width M now, this as an integral of this against the measure rho of W. So you should think of rho of W as a Dirac delta function at every Wj. So you should think of rho as like this. So then when you integrate rho against random feature of this type, you get back summation j aj sigma wj dot x. So sort of, you can also again view this as a linear in the a linear model, if you like, in the feature space, this one, where W has index set on the sphere. Now we need to start talking about what norm or metric to put on rho. These are infinite dimensional linear models. So you need some form of complexity control on rho. There's two very natural ones that people have looked at in the past. The first is to put an L2 norm on rho. This results in an RKHS. I'll call this F2 of B. The other one is known as, I'll call it F1 of B, is where you put an L1 norm on rho. The former, this is essentially a kernel method. It's a special case of an NTK. It's a type of NTK. What's the symbol like a bridge? This means like this means I'm ignoring. Just think of this as like O tilde of dr. I'm ignoring some logs and some other things I don't think are important. Okay. So let me say a few words about this F1 of B. So it's a Banach space. It's no longer a Hilbert space, meaning it's not a kernel space. And it promotes sort of, you can think of L1 norm as a sparsity, but in this feature space, sparse over this feature space. So let me say what is known for these two spaces. If you use weight decay on a two-layer network, you are implicitly optimizing over the space F1. If you work on sort of the mean field regime, that's also sort of in this F1. And sort of a lot of these implicit regularization works, mean field analysis, they try to all kind of implicitly, they're working kind of on F1 because the natural normalization there is to think of rho as a probability measure or signed measure. Okay, the sample complexity of F1 is well understood. It's sort of the norm of your ground truth in the F1 norm squared times some poly D factors over epsilon squared. So F1 has excellent statistical properties. It's pretty easy to see if that like you have a degree Q polynomial and the polynomial only depends on R of the D variables. U is an orthonormal matrix, sorry. Then your sample complexity is like the dimension times R to the Q. Okay, so remember kernel method was D to the Q and we went to R to the Q, roughly speaking. Right, so that's R to the Q is excellent. If you could do this, that would be amazing. And if you could use this F1 inductive bias, F1 norm, if you like, to learn teacher networks, your sample complexity would be like D times poly R. So certainly this would essentially get almost like the information theoretic optimal sample complexity, almost. However, F1 almost certainly cannot be efficiently learned since it includes all teacher networks of width R, of bounded norm. So all of those lower bounds I talked about on intersection of half spaces, juntas, whatever you like, all these things say, if you're trying to prove your mean field method or your implicit regularization learns all of F1, gets the global min in the F1 norm, that's probably impossible. So in my opinion, it's highly unlikely that mean field or any SGD approach or any algorithm at all will give polynomial time learning of F1. Sort of F1, the space is it's just it's intractable in terms of computation. So on the other hand, F2 is somehow the opposite. F2 is sort of like the opposite. It's computationally efficiently learnable via SGD. It's also learnable via the kernel method. However, it's kind of oblivious or ignorant of any low-dimensional structure. Again, if you look at the same kind of teacher functions or ground truth, P of Ux, then you need D to the Q, even if U only depends on a single variable. this teacher network has something like exponential or possibly even infinite F2 norm. And the sample complexity of, for example, learning a single ReLU with this F2 inductive bias with this kernel method is something like d to the poly 1 over epsilon. So truly a terrible result. And this is a terrible sample complexity. If my sample complexity like this, that's no good. So essentially, F2, is the same as NTK. NTK is no better, no worse, as far as theoretical bounds go, in terms of sample complexity. Okay. So kind of for the rest of this talk, what I want to talk about is how to find this sweet spot. Find an in-between space that can adapt to low-dimensional structure like F1 can do, but is computationally tractable via SGD. The obvious guess here, I would say, is to look at LP spaces, but I don't think this leads to tractable algorithms. In fact, there's a recent paper by Montanari's group, and if you work through the results, it kind of suggests that with L1.1, what you need to approximate L1 is you need something like L1 plus 1 over D. But then what they were only able to show something like you can get polynomial sample learning for L1.1, some constant. Okay, so there's a huge gap here between 1 over D and some constant. So it doesn't seem like LP is computationally tractable for P very close to 1. Instead, we can turn to a different way of viewing the problem. Let's turn to something we know how to solve. Let's look at when the activation function is a monomial. Let me look at the simplest case for motivation. The simplest case is when it's simply a quadratic activation. In this case, F2 corresponds to a Frobenius norm of inductive bias on the matrix, on this matrix. So F2 equal to, let's call this F of X. This F2 norm is equal to Frobenius norm on this M. And M nuclear is equal to F1 norm. Okay, good. So in this simple case, we actually do know how to get SGD to learn the nuclear norm. That's actually quite a simple thing. And it suggests that rank is a good measure of low-dimensional latent structure, simply because, we know that low nuclear norm corresponds to low rank. And for a monomial activation, the rank is equal to the width of the network. Okay. So let me motivate a different class of functions instead of two-layer teacher networks. This is very much motivated. What you do is you take the teacher networks, take all of their ReLUs, and change them to just monomials or polynomials. So a low-rank polynomial is of this form. It's a linear combination of w dot x to some integer power with some normalizations that I won't get into. Okay, so why is this a good class to study? So if you have teacher networks with polynomial activations of bounded degree, or like analytic activations like soft plus, or smoothed out ReLUs, these are all approximately polynomials because analytic functions you can truncate at log 1 over epsilon degree. Constant depth teacher networks with polynomial activation for the same reason. And sort of the real reason is I can show you a non-trivial learning guarantee with SGD for this class of functions. So let's turn to sort of again, calibrating what is a good approach here. What is a good result, what is a bad result, and what are we aiming to beat? Okay, yeah. Sort of the baseline approach, kernel method, NTK, F2, any kernel method, in fact, it's known. If you want to learn this entire class in a minimax sense, you need D to the P samples. That's a terrible result. Okay, like let's just assume all of these P's, let's just assume for the rest of the talk, P sub S is just P, right? So this is now a homogeneous polynomial. D to the P is terrible. That's basically like just taking and treating homogeneous polynomials as a linear space in the Kronecker space. So this is kind of just trivial as far as statistics goes. If you use F1 to learn this, you need something like D poly R. So essentially optimal. I'm not going to care about poly R factors, but this is computationally inefficient. Like exponential in dimension time. There's nothing known that's better than exponential in dimension time. And some earlier work by me, my co-author by Yu, we showed using what we call the quadratic NTK technique, you need D to the P minus 1 samples. So a very tiny improvement on D to the P, right? We took off one factor of D. So like, P you can think of as like 10 maybe. That's a reasonable thing to look at, to say I can approximate my activations by degree 10 things. So think of P as a big integer. I shaved off one factor. That's a very minor improvement. So this is a huge gap, right? D times poly R versus D to the P minus 1. The one I want to talk about today is trying to close this gap. Right. So the theorem I will kind of sketch out how to prove. It's too difficult, I think, to prove in a talk, but what we proved is that SGD plus with this sign dropout regularization technique on a 3-layer neural net architecture of polynomial width needs D to the P over 2 times poly R, ignore this P, over epsilon 4. The data assumption is you need some moment assumptions on X. They're not that strong. Any Gaussian like X from anything like this is fine. For any sigma with constant condition, anything like that's fine. And it doesn't need to be Gaussian. But the assumptions are not the easiest state, let's put it that way. Let's look at how to do this. Let's look at what our 3-layer architecture looks like. It's standard. It's a 3-layer with ReLU activations. In fact, for the proof, I do not even need to train the V's. I'm just going to randomly initialize and fix them. The result holds if you train them, but it doesn't help. Like our proof does not improve from training. It does not leverage it, I would say. But it is crucial that we have a 3-layer architecture. Our results are not attainable with only a 2-layer. Now we have a lower bound in the paper that kind of shows why this is not possible. And what is the algorithm? The algorithm is a little bit, is this SGD with a data-dependent regularizer. So remember, this is the definition of G. The G of X is going to be activation VL dot X plus B. These are randomly initialized and fixed, right? The V's are not trained. The V's and B's are not trained. You're going to estimate the covariance, the empirical covariance of the sigma hat. And then you're going to use this SGD and sign dropout algorithm used in these previous papers with this data-dependent regularizer, right? So the important thing here is to do this data-dependent regularization. The sign dropout is basically you multiply the gradients by plus minus 1. In regular dropout, you do 0, 1. It kind of prevents the model from memorizing. It prevents sort of this NTK memorization, which gives a bad sample complexity. And another benefit is it lets you use much larger learning rate, which potentially allows for better regularization. Okay. So let me give a proof sketch. The proof is a little bit complicated, so I'll give a simple case. And the target function is just a single monomial, beta dot x to the pth power. And hopefully you get the idea here. And I'm going to assume in this proof sketch that these are just Hermite polynomials of degree p over 2. Okay. So I'm going to have initialize d to the p over 2 of these. And then using Hermite polynomials, I know that I can write any beta dot x of p over 2 as theta dot g of x, right? Because I have a full basis. The Hermite polynomials from a basis of degree p over 2. Thus, on my last layer, or second hidden layer, all I need to learn is the square function. This quadratic NTK from Bai and Li and Alan Zhu's and Li and Liang is very good at learning quadratic complexity. Like Bai and Li, what we proved is that to learn quadratic functions, you only need d samples instead of d squared. And by applying that to degree p over 2 things, that in fact gets us this very large improvement of going from, so we've gone here from d to the p to d to the p over 2. This square root improvement, so we basically square rooted this. This square root improvement is sort of this magic in the quadratic NTK that can go from d squared to d, but actually it's not -1. You should think about it as a square root. It's more accurate. There's many potential improvements here. One minor improvement is that the epsilon dependence, I think, is loose. It should be epsilon squared. Right now we can prove epsilon 4. You can kind of hope that by training the first hidden layer, it kind of does a feature alignment or correction process to improve this result. I don't know how to prove this yet. I think it's doable, but yeah, I don't know how to do it yet. Of course, the bigger question is poly D possible? There's some reasons to actually believe, based on tensor completion and lower bounds in planted clique, that it may not be possible. So you know, whenever there's a lower bound, it just means you need more assumptions. So you can kind of hope that maybe, and also, you know, d to the p over 2 is still not great, right? What we want to go is to something like poly D. And to do this, we need more assumptions, like some sort of hierarchical assumption. Like first, you somehow learn these GSs, then you learn how to apply polynomials to these. And this itself is a low-rank polynomial. So then it can kind of be recursively chained together and learned. So if you can do this, maybe you can eventually get to poly D. I don't know. This is wishful thinking. And perhaps like, maybe if you saw these as part of the input, like some sort of ResNet structure, this would be even easier. Okay, so that was the last technical theorem I wanted to present. I wanted to leave you with some concluding thoughts, my thoughts on this area. So sort of, the goal is sort of a systematic understanding of SGD as applied to deep learning non-convex optimization. So for the only generic tool we have is linearization, which reduces it to convex optimization. The category 2 is also very systematic, but as far as I can tell, we've kind of understood most of the problems that category 2 can address. Maybe there's still a few more that we missed, but probably not a lot. So basically, what we kind of need to figure out is like how you can exploit assumptions on Y conditional on X. This is sort of what we're very bad at. Category 3, you can keep writing papers about it. It's doable, but they're pretty ad hoc and fragile. And there's so far no general pattern to these when you can use these. They seem like very one-off. And also, almost all the analysis I know of is not using anything about like P of X itself having potentially low dimensional structure. Like, for example, if your input were images and you can assume your images came from a GAN, is that helpful? I don't know. And finally, you know, how do architecture design, optimization, tractability, and regularization, which controls, this is essentially statistical. How do these interact? How far can we push our understanding of SGD for why deep learning is feasible? And once we know why, how can we make deep learning better? And understanding, of course, finally, not just simple classification, deep learning is successful widely. Self-supervised learning, representation learning, transfer learning, domain adaptation, and reinforcement learning, its abilities to impact all of these areas are really more due to representation learning than just its classification ability. And that's something that I didn't talk about at all today. And hopefully we can start to work towards that. And that's all I have to say. Thank you for listening.
Okay, this is Yanhuan. Thanks, Jason, for giving us a very state-of-the-art introduction to modern theory of deep learning. Jason, I think you can start with answering the questions in the chat window in our
Sure.
Zoom. Yeah. I think the last one will be very, very easy.
Yeah. So, for example, what are deeper? For example, you could think of something like this as a deeper network. Like,
excuse me, Jason.
Yeah.
I think we need to restate the students' questions.
This question is, what are deeper teacher networks?
Okay.
For example, right, something like, you know, this could be a valid teacher network. And you may hope, although no one knows how to prove, if this were some polynomial or monomial, that this is learnable. And this essentially corresponds to like this model. So I think that answers that question. The next question is about why GD is slower in adversarial training. Essentially it's asking about what you can say about GD in the context of adversarial training. I don't have too much to say about adversarial training. We do have a paper, my student Reichi Gao and I, Gao, Kai, Wang, and Shea and Lee. We have a paper using linearization method that proves the convergence of adversarial training. I don't know why it's slower in practice. I imagine it's just because you have to compute the argmax. And, you know, usually, min-max optimization is just slower by virtue of every time you have to recompute the max. That makes it much slower. Then Moritz is asking, how does it relate to other optimizers apart from SGD, such as Atom? Let's see. Right, that's a good question. So everything I said about linearization, I believe would apply to Atom. I don't think there's any fundamental difficulties there. I can't think of a reference exactly, but I'm sure it's doable. And the part about going beyond linearization, I don't know yet how to do that with Atom or adaptive gradient methods. In fact, I mean, I think the interesting question here is not how you can show the same things with adaptive gradient methods. Probably the right question to ask is, can you prove adaptive gradient methods are faster than SGD? Kind of showing that something is as good as the baseline, that's not a hard thing usually. You kind of would want to show it's better. Chun Hong is asking, I noticed that random initialization was used. Does this mean initialization has little effect on the results? I think for all of the results I presented today, except the random matrix part, can use any initialization. The random matrix theorems did use random initialization. It's not very crucial. Oh, no, that's not correct. That's not correct. No, I'm sorry. No, it's important random initialization is used. I forgot that there were some parameters in the second result that were fixed at random initialization.
Jason, please avoid using the slides in the Q&A session. The slides are not shown in the live page.
Oh, I see.
Yes,
Yeah.
right. Thanks.
I see. Yeah. So in the 3-layer network result about learning low-rank polynomials, random initialization is important there. But it's not much of a limitation. I mean, it's used every day in practice. LeCun, Kaiming, these are all random initializations. I think that's all of the questions.
Okay, then okay, I have some more general questions. Okay, the first one is motivated by an undergraduate student. Recently, an undergraduate student asked me, how far are we from being able to analyze the effectiveness of AlphaGo? What's your opinion?
Oh, of AlphaGo.
Or you can replace it with deep reinforcement learning. Perhaps it's more precise.
Oh, okay. I mean, the challenges in reinforcement learning are kind of, there's several challenges, right? So reinforcement learning, you can roughly divide into 2 classes of challenges. One is statistical. Like in online RL, there's sort of just sample complexity challenges. And that's kind of completely unrelated to what I talked about today. So I won't say much about them except to say that, this is, I think, probably Chaba already talked about these, I imagine, except to say that, everything is hard in reinforcement learning. Like the number of models you can learn is, forget the models I'm talking about today, even linear things are hard sometimes. So like the theoretical mess, it looks bleak in terms of theory for RL. But then, that's if you make these kind of standardish assumptions. If you're willing to go out of the box a little bit, you can kind of implicitly make assumptions like planning horizons are effectively small, or like if you're willing to work in simulator models, then some things start becoming tractable. We have some recent work just on arXiv last week about combining reinforcement learning with 2-layer neural networks.
Whoa.
So,
okay.
So at that level, it is possible if you're willing to make some assumptions, like what I said today about condition numbers and realizability, things are possible, and simulators. Simulator is crucial. So in online RL, I kind of imagine it's hard. However, on the good side, on the positive side, all of the optimization stuff I said about linearization, that combines beautifully with Q-learning, deep Q-learning, TD methods, policy gradient. You can kind of just plug and play. Like, I kind of forget, like Zhaoran Wang and Zoran, and I was involved with them on some of them. They have many papers that show you how to combine linearization in reinforcement learning. So that part is pretty doable. Now the question is, can you show neural net improve sample complexity? So kind of like, again, the goal you would really want to show is something like, if I do Q-learning with a kernel method is worse than Q-learning with a neural net. There's no result of that type yet. I think that maybe is, I don't think that's impossible. I think that it's just, I think no one's got, I think it should be doable. That would kind of be like category 2 or 3. Like right now, these are the equivalent of like, these correspond, I'm not supposed to use a slice, right? The things I just said about using linearization in policy gradient or Q-learning, those I would call category 1, is you're just showing like, you can linearize networks and they do as well as if you did kernel learning with Q-learning. That's good. That's a good first step. But then category 2 would be showing you can do better than the kernel plus Q-learning or kernelized policy gradient. That I predict, near future, 1 to 2 years, I think.
Okay.
Yeah.
Okay, thank you. Thank you for the answer. Okay, now I have a general question, required by the MLS staff to ask you. I know your PhD is in statistics. And did you encounter any challenge when switching from statistics to machine learning? Or do you think is there any essential difference between statistics and machine learning?
Let's see, right. I think the traditional answer has been that statistics has paid less attention to computation and algorithm design than computer science. I was lucky to have studied at Stanford, where I think this is not really true. In a department, where I think in the statistics department at Stanford, computation was always treated as a first-class citizen, if you like. So for me, the transition was not very difficult at all. Even in my PhD, I was paying attention to computation. I mean, there are some things you had to change. Like you have to work faster in computer science. In statistics, you can work slower. Yeah. There's like some style things like that.
Sure.
Culture things. Yeah.
To me, during my first years in PhD, I was also working in statistics, and my feel is that it was quite difficult for me to change the way of thinking. The way of thinking in statistics and in machine learning can overlap, but in general they are not exactly the same. And how do you feel about that?
I think I would say the questions they ask are almost the same, at least to me. I don't really distinguish in my own research. I don't think of oh, this is a statistics paper, that's a machine learning paper.
Sure.
To me, I think of them all as statistical learning. But I do agree, the two cultures have different ways of approaching the question, and perhaps what is the way to say it? And they bring different tools to the problems in some sense. Yeah. But I think the questions, they're roughly they're the same. Maybe like the training is different, so the tools are different.
Yeah, sure. Okay.
Yeah.
I saw there are 2 additional questions in the chat box.
Yes.
Them and then end this session.
Sure.
Okay.
Yurong Zeng is asking, is there any chance to do manifold learning or generative task with deterministic NTK? I don't know what deterministic NTK is, so I'll just assume it's NTK. And then, is there any chance to do manifold learning or generative task? Okay, so this must be two-part, different question. Sorry. Manifold learning. So manifold learning is usually an unsupervised learning problem. Like I usually think of manifold learning as like just, your data lies on a manifold or several manifolds, and you want to learn a metric or distance that respects like the intrinsic distance. I'm failing to see the connection to NTK at all. So I don't know what to say there. Or generative task with NTK. Yeah, I also don't know what that means. I think I'm going to give up on this question. And then Chun Hung is asking, is the random initialization purely random, or it follows certain pseudo randomness? Is there research on this? So I just assumed it was actually random. Of course, in practice, it comes, it's pseudo random. Of course, on a computer, it's always pseudo random. And yeah, there's definitely, cryptography or, some area of TCS studies this. I don't know anything about it. I'm sure they have theorems saying like functions of pseudo-random equal functions of random in some distributional sense. I'm sure there's theorems of like something of this style. I don't know any. I'm sure you could find a theorem that said this. And I think that's all for the questions. Yeah. Is it? Yeah, I think that's all.
Yeah, I think so. Okay, thank you, Jason. Okay, then let's end this session. And everyone, please notice that there will be an industrial talk in the afternoon, and also a lecture by Professor Arthur Gretton afterwards, after the industrial session. Okay, thank you, everyone. Bye-bye.